Good morning and welcome to my presentation of my graduation project to opt for the degree of licentiate in computer engineering. The project is called Invasive Checkpoint and Restart with iMPI applications, and it was possible in cooperation with el Instituto Tecnológico de Costa Rica and the Technische Universität München here in Germany. First, the agenda for today is as follows. I will provide a brief introduction where objectives and goals for this project are laid down. Then the method of resolution used during this process of this project is presented. Then the invasive checkpoint and restart system is presented and introduced in a brief description. After that, the test case and environment are described and the results are detailed. And finally, I will present some conclusions from this project and some future work. The objective are defined as follows. The general objective is to create a framework that provides fault tolerance to applications using remote direct memory access operations over the checkpoint memory region. And the specific objectives are: first, design a checkpoint and restart system that provides fault tolerance to applications running concurrently in the supercomputing center, and implement that system for a simple resource-aware application which enables remote direct memory access over its memory region. Also, the goals for this project are: this project works as an initial design and implementation of the system that should support resource-aware and common applications in a fixed number of nodes assigned to the system, where the checkpoints are saved in memory. The target system is a SuperMUC NG from the Leibniz Rechenzentrum or LRZ here in Munich with an Invasive Resource Manager or IRM. To test failures and adaptability, there will be an emulation of using IRM with shrink and expansion operations in terms of the number of nodes assigned to the system and to the applications in runtime. One of the requirements for the design of the system is its scalability. Since this project functions as an initial step, it's important to consider future possibilities and apply them in the design, so adding features becomes easier. For this, the development process fits with the cascade method. At first, a strong design phase where the structure of the system was defined to allow for future features. After that, there is a strong implementation phase, and it was developed to, and it was performed to develop the goals previously described. And finally, a testing phase to verify the functionality and the achieving of set goals. But before describing the system, there are a few concepts that are required. First, we are going to define what's a checkpoint or data set. And this is defined as a collection of data objects from MPI processes. Each data set is private to each MPI process. Data objects are an abstraction of data structures, just like a scalar variable or arrays. These data objects are also private for each MPI process. The checkpoints are also, before sending them to the iCheck system, they are gathered in the leading rank and stored in memory. Also, iCheck consists of four main components. First, the controller manages resources system-wide. The manager controls resources node-wide and launches the agents depending on the instructions of the controller and the application's requirements. The agents transfer the checkpoints between the application and iCheck. As well, there is a library that provides the procedures to handle and transfer the checkpoints. Here we can see the high-level architecture where the controller functions as a singleton entity. It's executed in just one node, and it will maintain that condition throughout the existence of the system, which is assigned to the iCheck. And it's the entry point for the applications. The managers are dynamically executed by the processes. The managers are dynamically executed by the controller in the nodes assigned to iCheck. and the agents are designed as an abstraction of processes. It's important to note that there is a limit on the number of agents running on the system, and it's based on the number of cores present in the node. Also, there are two types of messages for communication and checkpoint transfer, each one with their proper type of protocol due to efficiency. Communication messages are small, frequent, and variable size, so TCP is preferred. Checkpoints are larger but more scarce, from where the transfer benefits from the remote direct memory access protocol. Here, the rank 0, denoted with a dotted line in red, communicates with a controller to request resources. This is called the initialization operation. Based on those requirements, the controller will analyze the available resources and contact the proper managers to request the agents. The information regarding the agent will be returned to the rank 0 and then shared with the leading ranks denoted with a red line. When a checkpoint is ready to be transferred, the leading rank will notify the agent, and with the size of the checkpoint, since a fixed message size is a requirement for remote direct memory access, and wait for the transfer operation to be completed. The high-level architecture shows the capability of the system to work with multiple applications at the same time. But for this initial implementation, the system is only tested with one. Also, the system deployed in the SuperMUC NG uses Intel OmniPath 100. This is a proprietary architecture from Intel as a high-performance communication architecture that focuses on low power consumption and high throughput for exascale computing. This architecture provides a bandwidth of 100 gigabits per second or 12.5 gigabytes with error correcting lanes. As well, we use the remote direct memory access, which is a single-sided high throughput and low latency protocol to access remote hosts' memory, avoiding the operating system. It provides the operations to retrieve and write a checkpoint from the application's memory space with the option to do it asynchronously. LibFabric is an user-level API developed also by Intel that provides support for the hardware present on the SuperMUC NG with RDMA capabilities, but also provides portability to the code since the library is built to support another hardware different from OmniPath that also supports RDMA operations. It's important to note that not only RDMA, but also LibFabric are open source. The tests were performed differently than expected, since in May, a hacking incident affected around 8 of the largest supercomputers in Europe, including the SuperMUC NG, and it was shut down until almost half of June to correct the security issues. Based on this incident, we shift the testing from the SuperMUC NG to a desktop computer with server processors, where 8 virtual machines were created, with 4 cores and 1 gigabyte RAM each, based on Intel's Xeon Gold 6238 processors with 22 cores and 44 threads. The consideration of 8 virtual machines is due to the version of the Invasive Resource Manager that was installed on the system, which was configured to handle that number of virtual machines. Also, since the focus of this project was on functionality, the number of VMs was trivial. After this, I'm going to present an example application in pseudocode, but before that, it's important to clarify some auxiliary functions that are going to be used to understand the test application. First, create checkpoint is called when the application will add variables to the data set and then signal the agent to begin transferring the checkpoint. Recreate state is used in a restart operation when the application or node launches again. It will check if the checkpoint exists, and if it does, it will restore the values to the proper variable or all variables, depending on if the user uses a restore all approach. App adapt is used when there is a change in the number of nodes assigned to the application. Not only updates the variables associated with the MPI job, but it will also update the information from the library in terms of the number of nodes used and the respective agent information to keep a consistent state throughout the execution. So then the application, the resource-aware application, will begin with the initialization of the MPI structures and the library iCheck once. This can be seen in line 1 and 3. The status field is used to indicate to the library if the processes are joining or they are new. A joining state is produced when the invasive resource manager gives more nodes to an existing MPI job. So the processes join the current execution state. If there is a joining node, it will adapt and then check if there is a checkpoint. If there is, the library will restore the values stored in the checkpoint. Then the main loop is reached. Here, the application will constantly check with the IRM if there is a pending adaptation. This can be seen in line 26 with check adapt. If there is, it will adapt the information in where we have two types of adaptation. We have shrink and expansion. Shrink means that the application loses a certain number of nodes, and the expansion is when those resources that were taken away are reinstated. There are multiple scenarios, but this project focuses on the one where the number of nodes retrieved matches the number of nodes given back, also due to checkpoint consistency. If there is an expansion, the application must retrieve the checkpoint and restore the values. This function is a collective call with the other one present in line 9, as can be seen here. Since our focus is also in the memory consistency, the application will not create checkpoints if there is a node loss, because the checkpoint must be the same for all processes at any given time. When the loop counter reaches 80, it will exit and finalize. Here, there are two options to disconnect from iCheck system, by persisting or deleting. Persist will maintain the related resources to the application in the system alive for future execution. Delete will erase all the related resources, and if a subsequent execution is present, the system will allocate new resources for the application. Before going to the results, I'm gonna show you a video of the system working. Here, the controller is gonna be launched, and then the manager. Here, the manager has registered in the controller, and then we will launch the application. The application is launched with 16 processes. Given that we have 4 cores per node, we are using a grid structure or 4x4. The library is requesting information of the agents, and it's returned to the agent, to the application, and then it will loop as seen in the application. And then it comes the shrink operation. Here we can see the shrink operation, which is the result of the invasive resource manager. This is the output. And that's the adaptation of the library. And then we can see that the operation is done with 3 nodes. After some time, the IRM will return those resources. Here, there is the expansion. Actually, you can see here, request adapt children ready, which is also an output from the invasive resource manager. And here, there is the adaptation of the library. And it will continue with 4. And that behavior will maintain through the life of the application. So, which are the results? The system was run 170 times, from which 30 tests were successful. The failure source source was not the system itself, but rather IRM and iMPI. This means that the success rate goes from 17% to 100%. The 145 failed tests are due to the incompatibilities of IRM with invasive and non-invasive applications. The test applications use the procedures, mainly SRUN, given by IRM, to execute it in multiple hosts, as parallel applications are intended. But also it takes advantage of the adaptation procedures provided by IRM. On the other hand, the controller uses only SRUN to execute the manager in remote hosts, but they are not designed or implemented as a resource-aware application. The mixture of two different types of applications, invasive and non-invasive, violates the purpose of IRM, since it's focused and designed solely for resource-aware ones. To fix the errors produced by IRM, the managers are launched manually, as you could see in the video, in each node, where they are supposed to be executed. Given these conditions, the test results were acceptable because the system functions as it's intended to be, and it achieves its goals despite the errors introduced by external systems to this project. To finalize, iCheck provides application-level fault tolerance to resource-aware applications by enabling checkpoint capabilities on them using remote direct memory access operations over the checkpoint memory region. It also provides adaptation support, as well combining invasive and non-invasive applications procedures, produces runtime errors due to the design of IRM. Performance tests are not included due to the virtual test environment, and the agent does not retrieve the checkpoint from the application since the test hardware blocks RDMA reads. The task of transferring the checkpoint from the application to the agent is handled by the library. So, also with what could be the next steps for this project? First, the project will need redistribution support. This means that the checkpoint will be distributed to the remaining agents if there is an adaptation. Also, we want to include mapping for variables. This means that there are variables that are shared across processes in an MPI application. So we want to provide a structure for that. And also, we want to test environments where threads are included in the applications. In all, the system is designed only for single-threaded purposes. And also, we will provide testing in the system with more applications in a real supercomputer to provide performance measurements. Thank you very much. Any questions?